So the last of our substances we need to explain the properties of are our metals or metallic substances. Not surprisingly, the bonds in a metal are called metallic bonds. They are a really special bond, and that's why they've got their own special name. They are the bonding between the cations, the positive ions of the metal, and the sea of valence electrons around them. The fact that each positive metal ion has got in a relationship with multiple electrons that have come from other atoms creates the metallic bond. It's non-directional. The attraction is in every direction, so in 3 dimensions. So this way, this way, this way, this way, this way, in every direction, it's attracted to that sea of electrons. And therefore, neighboring cations, positive ions, are attracted to the same space. So therefore, they're held in place really easily. So we call this a sea of valence electrons. Every single metal atom donates its valence shell electrons into the sea. But this one's electrons might not just stay here. They might end up over here and here. They move around. But that attraction to that space, that negative space that is our sea of electrons, that attraction to that space is what creates the metallic bond. Now, sorry, is the question there? Great. So, very good question. That's the next one we're going to get into. So, the metallic bond is created because those atoms become ions, but they still have the right number of electrons around them. They're just in that sea of electrons. So, in an answer, if you write metallic ions, you have to say metallic ions plus sea of valence electrons. You have to have both. But if you were to say, and you know those tables that that table we drew up where we talked about particles, if you don't want to write all of this, metallic ions and a sea of electrons, you just say atoms. Because actually, let's say it's iron, its valence electrons are all involved in bonding. They haven't gone anywhere. So it still is technically an atom. It's got the right number of electrons, the right number of protons to still be technically an atom. Okay, so the simplest way to answer an exam question is to say the particles are atoms, just like in our covalent networks. The difference here is that you've got metallic bonds, which are described as being non-directional, which means the attraction is in 3 dimensions, and they again create a 3D lattice, so that attraction is in 3 dimensions.
Are the metallic bonds stronger or weaker than covalent bonds?
They're stronger. So a metallic bond is actually very strong. It's an electric attraction. It's a positive to a negative. So it's a strong, strong bond. The difference is they're non-directional. Good. So the strength is around there with ionic. But ionics are directional. They are attracting 2 things and just that straight into each other. Whereas these ones are attracting everything around them. So it's more like thinking about the sun attracting the planets. They're orbiting, and that gravitational field goes in 3 dimensions. Everything in that gravitational field is pulled towards it. But they can move. The planets can orbit. They're not just being pulled straight into the sun. Whereas if we had a comet on a crash course with the Earth, now that's more like an ionic bond because it's coming straight at it and being accelerated more and more and more and more the closer it gets. So being non-directional, it's still a strong bond, but it's not directional, so it'll allow things to move. And this is the key thing. So we know that metals are ductile and malleable. Ductile can be pulled into a wire, malleable can be bent. So why is that? Well, even though these are strong bonds, they are able to be reshaped without breaking. So the electrons and the cations can all move relative to each other without breaking the metallic bond. So the reason for that is the non-directional nature of the metallic bond. If it was directional like an ionic bond, it would break, and so it would be brittle. They're still strong. They're still very strong bonds. So the fact they can reshape, the bond itself can reshape, it's not in a particular direction, gives the substance its ductility and its malleability. The electrical conduction, I think, is going to be quite easy now. We've done graphite in our previous video. So graphite had what sitting in between the carbon sheets? Cool, a sea of valence electrons. And again, we've got a sea of valence electrons. These are charged particles that can move from A to B. So the flow of those electrons is what gives our electrical conductivity. So the reason for our electrical conductivity is that thermal or heat conduction is quite different. The electrons are partially involved in heat conduction, partially, because it's an energy transfer, but actually it's more to do with these things. If I vibrate one of those, what's it going to do to the neighbouring ones that it gets close to? But good, it's going to vibrate. And why will it vibrate the next one? Look at the charges. Great, there'll be repulsion. So if I get these ones vibrating, these ones will vibrate pretty fast, which means everything neighbouring will. So because the cations have got a charge, once I start one lot vibrating, that's going to create a chain reaction.
I might have missed something, but why is it all positive?
So these are the atoms have lost their electrons, their valence electrons, into the sea of electrons. So it makes them positively charged. So for example, iron would lose 3 electrons into there. Sodium would lose 1 per atom. Good, and you'll notice that something like iron is stronger because it's got more electrons coming off than sodium, which is very malleable, you can bend it if you dare touch it, very, very easily because the bonds are not as strong, fewer electrons.
Is that what all the ones in missiles like, you know how there's like...
Yes, so on the left, well, sorry, most of the atoms are, but the left-hand side are your metals because they can lose electrons more easily and create a sea of electrons to create the metallic bond. Is that sort of what you're asking there? Cool. So them being a thermal conductor is to do with the fact that they've got cations which can vibrate and pass that on. Okay, so that's to do with the metallic ions. And to a lesser degree, also the sea of electrons. Electrons vibrating will also pass on that electrical charge. Sorry, heat will pass on heat as well. And their relatively high melting or boiling point is because its positives attracted to negatives. So you've got that electric attraction again. For an ionic bond, it was very high. We get the same thing. They're relatively high again because you've got a metallic bond between cations and electrons. Those are your base ideas, and then when we look at stuff in our side pad, we're going to be able to look at how we use this as an answer for a question in NCEA. Are there any more questions while I've got this still filming?